This was just verified by the chair that this is indeed the last colloquium. Yeah, Amin said a couple of times, Hartmut, are you sure? Are you willing to make it? Okay, yeah, we are very happy to have Vladan Vuletic here. Vladan did his undergraduate and graduate education, I think also high school, right, in Germany. And in particular, he worked in a group of Ted Hensch. You all have heard of his work. And he actually, both for his diploma and his PhD, he got summa cum laude, which is really exceptionally. He moved then to Stanford as a postdoc to work with Stephen Chu, and that was in 1997, and then in 2000 he became an assistant professor, and then in 2003 he actually left this position and went to MIT to become their first assistant professor, but he climbed up through the ladder and is now a full professor there, working on quite a variety of topics in AMO. For instance, he's well known for cavity QED experiments and also having photons interact. So if you didn't know that, they can actually interact via another medium, and also entangling neutral atoms. But today he's going to speak about trapped ions. And actually, I forgot this, that he has, of course, also won a number of prizes, and I want to particularly mention the Outstanding Referee Award, and also from the APS, and also an award, Outstanding Undergraduate Research Opportunities Faculty Mentor of the Year. So, and then Alfred Sloan Fellow, he also won the Marko Jaric Prize, is that pronounced roughly right? And is of course a fellow of the American Physical Society. Today, Vladan will talk about how you can actually use trapped ions to at least get some idea of what is going on with friction. Please, Vladan.
For the kind introduction, as I will tell you in a moment, Hartmut is in good part responsible for what I will tell you about today. When I learned friction and when I started teaching friction, I found this very dissatisfying subject. I didn't really understand what was going on. And I was hoping today to draw some of you in with the question, what does the golden ratio have to do with friction? You probably don't know the answer. I didn't know the answer certainly 2 years ago. And you probably even didn't know that the question existed in the first place. And today I would like to tell you about it. My co-workers on this are Alexei Belinsky, Laurent Gangler, and Counts, and we're collaborating in part with Otto Roger from Seoul, from the University of Seoul. So what I will, the medium that we will use are ion chains, cold ions, that arrange themselves when they are inside the trap in a one-dimensional lattice, like you see here. Each of these blobs is an individual ion, and they interact with each other via Coulomb forces forming these crystals. And I would like to show you how this can be used to implement some long-standing models of friction with a far-reaching control for study. So we all teach or learn a few macroscopic friction laws. For instance, the friction force is proportional to the normal force. That maybe makes sense. If the mass is twice as heavy, it will press on twice as strongly, and so the static friction force is double. Already this fact that the friction force is independent of velocity is maybe a little bit surprising, that no matter how fast you move along the surface, the friction force is the same once you start moving. You of course know the kinetic friction force is a little less than static friction force. This one is really confusing, mainly the fact that when you take an object and you put it on a surface, that the friction force is independent of the surface area. And there's actually still debate going on to a certain extent why that is. Very naively, you might think that if the area is larger, there are more points of contact, so maybe the friction forces should increase in areas, but they don't do so. And I would like to show you and to re-examine all of these empirical macroscopic laws at the atomic scale. So maybe a word of caution from Wolfgang Pauli. Wolfgang Pauli was well known for being outspoken. You know, he's reported to have said, "This is not right. This is not even wrong." And he was really outraged about some statement being made. And so he had the following to say about friction of surfaces. He said, "God made matter, but surfaces were the work of the devil." And being a quantum physicist, who likes clean things, maybe we should be a little bit cautious about this. He had another saying that says, "Das ist ein Schmutzeffekt und Schmutzeffekten befasse ich mich." Meaning, this is a dirt effect, and I don't concern myself with dirt effects. This, in fact, he didn't say about surfaces, he said it about semiconductors. Okay, so maybe we can go a step back and maybe. Okay, so, but it turns out that we can predict, as physicists, we can predict hardly anything about macroscopic friction from first principles. So if I tell you, these are the two surfaces, can anybody in the world calculate for me the kinetic friction or static friction coefficient? The answer is no. We cannot even change friction by a little bit, except we can use lubricants. But given surfaces, we cannot even change friction by 1%. And yet there's this coefficient of friction that can be measured and defined. So physicists had almost left this field and left it to the engineers. However, this has changed a little bit. There's a renewed interest in what people call tribology, the study of friction. I would like to tell you a little bit why that is. And I think the main motivation is that chemists and other people are able now to build nanoscale machines. So they have built, for instance, this nano car which moves along the surface when you touch it with atomic force or an electron microscope. They can build nanomotors of various types, more than, for instance, 50 different nanomotors, molecular pumps, etc. have been demonstrated. And yet we haven't heard much about the impact of these nanomachines, and one of the reasons is that they're severely limited by frictional wear and tear. And the general argument is simply that, the surface to volume area scales as the size of the object, so when I make things very small, the surface is much larger relative to the boundary. That's the problem. To show you how bad this problem is, okay, maybe I'll do that next. So another reason for renewed interest is that now the computers are becoming better and better, and people start to be able to do molecular dynamics simulations from first principles, trying to predict things about friction. And at the moment, they can do so with maybe tens of particles at the surface layer. Also, there's been a big push from atomic force microscopy, so people can put atomic force tips and move them over surfaces, and they've been able to observe things like this, which represents now, here they're measuring the force as a function of position, and basically they have been able to measure stick-slip friction on the atomic scale. Each of these slips is, as the atomic force microscope slips one atom over. So there has been a lot of work in this very interesting area. And for us, one of the reasons, well, one of the main reasons actually, we are able to do this is because Hartmut Hefner was one of the co-inventors of a new system to simulate friction with much further reaching control than is actually possible in atomic force microscopy. And he did this work, and this is how we first learned about this possibility. So I'm very indebted. So going back to the question, how bad is friction at the nanoscale? Let's take an example. Here's a quantum physicist driving a car, and while he's driving a car, he starts thinking how bad friction really is. So he thinks about his tires, and he wonders how bad is friction. So he takes an envelope and starts to do a back of the envelope calculation of the friction or wear and tear. So he says the following: my tire maybe loses a millimeter or so every 5,000 kilometers. That's like a reasonable guess, right? Given how often I have to change my tires. So that means an atomic layer, which is something like 2 angstrom thick, so that 1 millimeter is 5 million atomic layers. So every 5,000 kilometers, the tire loses 5 million atomic layers. I'm guessing that the circumference of the wheel here is something like a meter, right? It seems reasonable. So 5,000 kilometers is therefore 5 million rotations of the tire. So when you compare these two, you find that as you're driving your car, you're leaving 1 atomic layer on the surface on average behind. Right? For a tire, it doesn't really matter too much. You have to change your higher every now and then, but for a nanomachine, this is of course disastrous, right? If a nanomachine consists only of a few atomic layers, clearly losing frictional wear, where you lose an atomic layer every so often will just kill the machine. And so it's a really huge problem. Okay. So what I would like to tell you about is, first is a warm-up, a very old model of friction, of nanofriction. It's a single particle model going back to the 1920s by Vladan and Thomas, and how we realize it in our system and use it as a benchmark. And then what becomes really interesting is what happens when you take more than one contact, more than one atom as a contact layer. And this is described mathematically by this famous Frankel-Kontarova model, which applies in many fields of physics. And I would like to show you many particle results in this regime, and I would like to show you that in this regime, the results are really not very intuitive, even though all that I will be talking about today is classical physics. Okay, classical physics, potentials, and spins, and so on. And then I would like to tell you a little bit about what happens to temperature, the velocity dependence of friction. You will see that at the nano scale, it's not as simple as at the macro scale. And then connect the whole thing to a famous transition of mathematical physics to supercomputing. Okay, so that's the plan. And as I said, this work that we are doing is based on theoretical proposals by Shepelyansky, Tosati, Heckman, and others. And we really learned through this about this possibility for hardware. Okay, so what does frictional surface look like? We are interested in nanofriction, so we think of it as some kind of substrate layer here. Then we have this object that is moving on the substrate, and there's basically a surface layer shown here in red, and then there's the bulk of the material. And so basically we think of this as this substrate providing a form of periodic potential for this surface layer, and then this chain of surface atoms, they are connected with springs to the support and with springs to each other. So the way you realize that in such a system, it's very hard to know, for instance, how many atoms does your contact really consist of, or other things, and how are they sliding. So we're going to build a model system for this, an emulator, if you want a simulator, and it will consist of individual ions. So the ions will be the surface layer. We can trap any number from 1 to something like 10, because it's going to be up to 6 ions in this. And then our periodic potential that comes in the real system from the substrate will be now coming from a light standing wave. And this is nice because it blows up the scale from angstrom size to something like 100 nanometer size, where we can actually resolve the individual ions and see where they are relative to this optical potential. So we can watch them slip one by one at a time, because this is a much larger scale. And furthermore, because we have a far reach we are doing this at cold temperatures, we can control the temperature of the ions, we can control the depth of the potential via the strength of the light field and so on. Basically, we can control every parameter. And you might ask why ions rather than neutral atoms. So it turns out that it's very essential to have interactions between the ions. So the model becomes really interesting when the ions are interacting, and you can think of these as simply springs connecting the atoms in this subsurface. So our real experiment looks like this. We have a chip that we use for tracking the ions and laser cooling them, and then we have an optical resonator that we use to enhance the optical light field to form this periodic structure of the standing wave. And we can make large crystals, although all our measurements are done with up to only 6 ions at a time. So how does this friction work? Well, this is the first model, and a very simple model going back to Thomas of basically one atom making the contact. And the picture here is that we have this periodic potential, which comes from basically the substrate. This is the atomic structure of the substrate. And then you have this one atom that's making the contact, that's connected to the rest of the object moving via spring force like so. And so what do you expect in the system? Well, you see something like the following. So what you see here is, if I combine the spring potential, which is a parabolic potential, together with the periodic sinusoidal potential of the optical lattice or of the atomic surface layer, then if this potential becomes strong enough, I have a bistable situation where the ion is, where the particle is prepared at one minimum, is pulled over, it stays at the local minimum. At some point, this local minimum disappears, and the particle moves to the next side, and it releases this amount of energy, which is taken away at speed. In the real system, this is taken away in the form of phonons or heats in the crystal, the object. In our case, it's taken away by laser cooling. So basically, this is how sticks to friction work. The particle remains trapped at the local minimum. At some point, it is released, and it releases this extra energy difference first. So this is how it works. So, as I said, this is our system. We use a trap, ion trap. We can move the ion around by moving the potentials on the ion trap, so we can basically translate this trap back and forward. And the atom or the ion is connected to the spring to this ion trap, because the ion trap is effectively a parabolic potential, and we can control all macroscopic parameters. And so, for instance, this is what we see with free particles. We can image the ions individually, so we can see where they are. And we can effectively, by observing how much light they emit, we can actually tell where they are relative to this periodic lattice, which has a period of 185 nanometers. So we can follow the motion of the particles as we translate them inside this optical potential. So let's see what happens for a single particle. This is basically the same thing that we've seen in the movie. What we do is we displace the ion linearly, we apply linear force versus time, moving the ion one way and then back. And so the ion is prepared, the particle is prepared in this minimum. It remains in the local minimum even when it's no longer a global minimum up to this point. At this point, it slips from this minimum that disappears to the new global minimum over here. And then it releases energy. And what we see is as the atom is recooled, it emits a lot of light. So when we pull the ion over, we see the fluorescence increase. There's a peak. At this point, the ion slips. And then it gets recooled in the new global minimum. And then the ion is pulled further. Here's another slip. And when we go backwards, what we see is hysteresis in the system. When we pull backwards, these two curves don't overlap in applied force. The ion remains now in this local minimum until it is released, it slips, it goes over there. So basically, this hysteresis is the measurement of the static friction force. How strong do I need to apply force in order to pull the ion out of the local minimum? And so this is a measurement of the static friction force. It's twice the static friction force because we're going forward and back. So this distance measures the static friction force. The ion fluorescence tells us where the ion is in the optical lattice. So this, we can convert it into a position diagram or a position. So overall, we can plot the ion position along one axis and the applied force along the other axis. And when we're going one way, the applied force is like so. The ion doesn't slip. At this point, it slips to the new global minimum. And when we go back, the ion remains first in the new position until it slips back. So this is just like in classical mechanics, the work integral FdX. Integral of FdX is basically the work done by the ion or the heating done by the friction force. So the area, again, turns out to be 2 times the dissipated power because we're going forward and back. So this area tells us the friction work done in the system, and this distance here tells us twice the static friction force. So the applied force is actually just displace the parabolic potential. We have a parabolic overall potential, very good question. And so as we displace it linearly in time, that makes the force grow linearly in time. Very good question. So this one we don't actually measure, we calibrate it. We see how far we move over and we measure the vibration frequency. It's a very good question, thank you. So please ask the question. This is relatively simple, so everybody should hopefully be able to follow. So we measure this and we can measure the friction. Now what do you see as I measure the maximum, for instance, the maximum static friction force as a function of the corrugation parameter? The corrugation parameter is simply the normalized depth of the potential, right? As I ramp this periodic potential up, I see that the maximum static friction force is not proportional to the normal load, which is the same as that of the potential, but it first remains 0 and then starts over here. Any ideas what this might be? So I'll show you a movie. So basically, if this periodic potential is not strong enough, then the overall potential has just one global minimum, right? And the particle just follows that global minimum. It jitters a little bit, but it just follows the global minimum. There's no fixed friction in the system. But basically, the condition is that this curvature of the periodic potential has to exceed the curvature of the parabolic trap in order to be a bistable system. Right? So basically in this region there's no friction force simply because there's just one global minimum. And then as soon as you go back to a deeper potential, now we have a new global minimum. This is where you start to see the friction force increase. Beyond this point here, we haven't measured so far, we're down now to 2 measurements. There are not only 2 minima, this is a bistable potential, there are actually 3, 4 minima and so on, and then new physics. But basically this is the prediction from the Crantor-Tompkins model, and we see it agrees very nicely from measured data. So this is kind of like a warm-up, the single particle, everything 6.3 is in the model. Now let's look at something more interesting and more complicated. Now let's imagine that we have a chain of particles, and this is basically Frankel-Contarova model, so we have particles, they are connected to each other via springs, and they are connected also effectively via springs to the object. So for us, these springs are basically the external confinement of the trap. This is the external confinement of the ions, and basically these effective springs are coming from the Coulomb interaction between the ions when it's linearized around small spaces. So we have now a string of particles that have springs between them and are attached to the string. And now it turns out that things, a new parameter comes into the system, and the new parameter is, on the one hand, you have the periodicity of the lattice, I call it A, basically the period of the lattice. And on the other hand, you have the intrinsic period of the ion chain, which I call D. And you could now think about that maybe things will depend on whether this D is commensurate or incommensurate relative to this A. Let's walk through this. So for instance, if we adjust the D to be commensurate with this length scale A, so basically that the intrinsic spacing between the particles is an integer multiple of this period of potential, then we see the following, in this case shown 3 particles. As we apply the force, now the fluorescence of the ions is in color, and we apply the force this way and then that way. So what you see is whenever it's red, this is the point in time or in force where the particles slip. And this is ion 1, 2, 3, 3 particles. And what you see here happening is basically they slip all at the same time. When we go that way, and then they slip all at the same time. When we go backward, and there's again a steady system, which measures the static position. So if I make the same plot as before, plotted for one of the ions, for instance, say ion 2, then I see basically the same situation as for a single particle. I pull, the particle remains in its old local minimum, it slips to the new local minimum. As I pull back, it remains in the new local minimum, it slips back. And so I see basically a dissipation, which is simply n times the single particle dissipation. I have a small movie to show you why that is. So here, the particles are commensurate with the lattice, and you see they all slip at the same time. They get basically pulled, and then they slip at the same time. And because the spacing between the particles doesn't change, these springs between the particles are really not relevant to the problem. They all are doing simply the same thing. Right? By the way, the stick-slip friction is believed not to govern only phenomena at the nanoscale. It's even believed to govern, for instance, earthquakes at very, very long scales. Something similar is believed to happen. So here you see it's basically kind of boring. It's just single particle physics all over again, even for string of particles. Now, I change the spacing between the particles ever so slightly so that they are no longer commensurate with the system. And we see something very different. Now I've changed the spacing between the particles. The particles are spaced by 3 microns. I change it by on the order of 50 nanometers or so. We are not really changing the spin forces. And now I see 2 things. First, if I plot this dissipation diagram, FDX, I see that the area is very, very small. It's tiny. So basically, ion gets pulled very easily and then makes a little jump, and as it comes back, it's pulled just a little bit and makes a jump back. So the dissipated power, the dissipated energy is much, much smaller than before. Also, if I look at the chain, and I look what happens, I see that instead of all of these ions slipping at the same time, as when they were for a commensurate arrangement, they are kind of slipping one by one. First ion 1, then ion 2, then ion 3, and backwards the same thing. So we see that just a slight rearrangement of the ion spacing dramatically changes the friction force between ions. And the way this looks, What kind of motion is this? This is almost like a kink motion. So instead of them all moving together, it's basically the first ion moves, then the next ion moves, then the next ion moves because of the strain forces between them. And this is what you see in this simulation. Here they are incommensurate, and you see that they move something like a caterpillar. The first particle moves over and then pulls the next one over and so on. So one way to understand this, what is happening, as the ion gets pulled against the potential, the energy gets stored in the spring reversibly. Before it was simply a release in the form of dissipation. In this case, the energy from this periodic potential is converted into spring energy that is then adiabatically converted back into the motion energy of the ions and basically the friction force is dramatically reduced. And this is all just a slight change of the configuration of the particles. So we can, for instance, now investigate what happens to this friction force as we change the matching of the ion chain to the periodic potential. Here is the logarithmic scale I'm plotting parameter. This parameter is simply the average force on the center of mass motion of the ion. So match means all the ions are in the same location of the periodic potential, so they see all the same force. And 0 would mean the particles are distributed in such a way that at the unperturbed position, the center of mass force is 0. Right? So basically the ions are maximally, have to see maximally different forces. And so what you see when we change this matching parameter from match to mismatch, then the mean friction force and also the dissipation drops dramatically. This is a logarithmic scale. And so for even 2 ions, the friction force drops by a factor of 10 or so. For 6 ions, it drops almost by a factor of 9. As I will tell you a little bit later, some of this is a temperature effect. The dashed curves are what we calculate for a real 0 temperature system, but even for a real 0 temperature, basically get a factor of 10 or so for 6 ions suppression friction. Now this came as a surprise to the theorists. So in the late 1980s, some theorists from Japan had predicted this phenomenon, and they had called it superlubricity. They had predicted that when you mismatch the 2 lattices, the friction force would be dramatically reduced. However, all calculations had been done for infinite chain, and it was believed that a chain of a few particles would not be enough to see this. So if you ask me, how many is many, I would say 3 is many, and 6 is plenty. And it turns out in atomic physics we have learned this in various contexts and other experiments as well. Very often, even for a few particles, things converge rather quickly. So how does this work? Let me give you an explanation. Imagine for the moment that the ions were connected by a stiff bar, by basically infinitely stiff spring, right? And if I arrange them in such a way that they both experience the same force, right, then of course I get maximum stiff friction. Now on the other hand, imagine they are still connected by a stiff bar, but I arrange them so that they always experience opposite forces on the lattice, right? Then of course there's no force overall on the center of mass motion of the particles, and you would not be surprised that there's no friction. Right? Basically, on this stiff system, there's simply no force coming from the periodic lattice. Now, the interesting essence of superlubricity is that when I replace this stiff bar by a spring to something that can actually compress, this so-called superlubricity survives. So even though now the force does not cancel because the springs can compress, it still leads to very, very little friction, even for the particles. So basically, this is this essence of superlubricity, the 0 friction persists in finite spring forces. Now let's re-examine one of the other questions. So one thing is, one message to take away is the friction force really depends very strongly on the arrangement of the particles for nanoparticles, right? Another question that we can ask is how does the friction force depend on velocity? And we know macroscopically we said the kinetic friction force is independent of velocity. So this is what we measure. In our system we can vary the velocity over a very wide range. So here it's a logarithmic scale, and we vary the velocity of the system by almost 5 orders of magnitude. And we measure the static friction force like before, what is the power. And so you see now that we see 4 different regimes. We see a regime of essentially no friction. We see a regime where friction depends logarithmically on velocity. We see a regime, this is relatively small for our parameters, where the friction is independent of velocity. And then we even see a regime where the friction, again, drops. So any guesses what this might be, this regime, for instance? So it turns out that this has to be the finite temperature of the atoms. And let me show you a movie. So again, I'm moving this bistable potential over, but now I'm allowing the ion to thermally hop over the barrier. I'm doing this transfer relatively slowly, so that at finite temperature, the ion can find always its new Maxwell-Boltzmann distribution. So basically, the ion will follow via thermal hopping always the global minimum. So if I move very, very slowly, there's no bistability in the potential because the ion always thermally finds its local minimum. And if this speed is very, very low, then simply there's no friction force surviving. So this is what is happening here. So basically that's this regime where the friction force is completely. So this is the regime where the transport speed, the time to move the ion one lattice side over, is much, much longer than the thermal hopping time, and therefore there's no friction force. Now this regime, this logarithmic dependence on velocity, is where the two are comparable. Basically, the time scale for the ion to thermally hop from one minimum to the other is comparable to the transport time to move the thing one lattice side over. And then you simply get a logarithmic dependence of velocity because the Boltzmann rate is exponential, e to the minus u over kT. So this is just a competition between the thermal hopping time scale and the velocity time scale. This is the regime that we are usually in with macroscopic objects, where basically the thermal hopping is negligible, and therefore we get the maximum friction force. Right? Here basically the friction force doesn't depend on velocity, because each time you move one side over, you release a certain amount of energy. And that's pretty simple. And then over here, this is the so-called underdamped regime. So in our situation, the ion, as it moves over, it needs to be recooled to find the new local maximum. And in this regime, the cooling time scale is comparable to the transport time scale. So effectively, the ion doesn't get recooled very well to the new minimum. If you want, the energy doesn't get taken away quickly enough of the phonons in the real system. And therefore, the atom or ion is effectively hotter than before. That's responsible for this part. And you see again, now I'm plotting for two different temperatures the same velocity curve. This is the matched case, and this is the mismatched case. So you see again that over all ranges of friction where friction is observable, the mismatched case, this is for just two particles, has substantially lower friction than the matched case. And one way to understand this is if I plot for two particles a new potential landscape that now includes all possible degrees of freedom for the generalized potential landscape. And in the matched case, basically I have two minima, and they are separated by a certain energy barrier like so. And for the mismatched case, basically these new two local potential minima are separated by a much lower barrier because the spring forces between the particles. And so even if you were, say, not infinitely cold, but very cold in this system at low temperature, so that thermal hopping was negligible in the matched case, it might still become non-negligible in the mismatched case, simply because if I have finite non-zero temperature here, now thermal hopping might be relevant. And that is the reason, if I go back for a moment, that is the reason why basically we see a strong temperature effect even at low temperatures, where for a matched case we see no difference between the particles. Here, this is what we expect would be equal to 0, and this is what we actually observe because of thermal hopping. So thermal hopping becomes much more important when basically the effective potential minima are separated by a smaller barrier. And this is the reference for superlubricity that was predicted actually 1993 that I told you about. So again, it was predicted for infinite chains, and the real surprise was that you can observe a sizable effect for just a few particles. And finally, I would like to tell you about the connection to the so-called Aubry transition, which is a static transition. So in the early 1980s, Aubry, a mathematical physicist, asked himself simply the following question. Imagine that you have a chain of particles, a chain of masses connected by springs, an infinitely long chain. And imagine I slowly turn on a periodic potential. And I'm interested again in the situation where this intrinsic distance between the particles in the chain may or may not be commensurate with this periodic potential length scaling. And he asks himself, what happens? So what do we expect naively? If the periodic potential is relatively weak, then basically the positions of these particles will be mainly determined by the spring forces between them. And their positions will be close to this distance scale. And then, if you make the potential very, very deep, at some point the periodic potential forces must win. right? And the particles will just localize in whatever the next local minimum is, right? And somewhere between them is a transition, and Aubry solved the question about the nature of this transition. And so what we found is that, so you might, for instance, naively expect that this particle that sits right on top of the potential might maybe localize earlier than these particles that sit on the slope, right? Because this is most unstable points that should localize here and there. What Aubry found is no, for an infinite chain, basically all of the particles localize at the same time. And the physics is, as soon as this one localizes, it will exert a force on its neighbors, which will force its neighbors to localize and so on. So that was one interesting aspect. They don't localize by one. At some critical strength potential, they suddenly all localize at the same time. The other interesting thing that he predicted is that they localize in an interesting way. So this is what I said before. They suddenly localize the periodic potential in some critical potential. So the other thing is that they localize in an interesting way that is basically fractal position distribution. I'll show you what I mean. So in this graph, I will plot the initial position of the particle modulo A. So basically think of this as the distance relative to the maximum. 0 means the atom is initially sitting right on top of the maximum of the periodic potential. And along this axis, I will plot where the ion ends up as I turn up the potential strength. Right? And so you see for some small potential strength, much less than its critical potential strength, basically there's a slight deformation of this curve. This curve will be a line if there's no periodic potential. And you see basically the ions are starting to avoid the maximum potential. And basically because I have an infinitely long chain, every one of these points on this line is realized somewhere in the system. Right? This is basically where the ion is. This is the commensurate chain. And every one of these points is realized. So let me show you a movie what happens when I gradually increase the strength of the periodic potential. So you see the thing first deforms smoothly, and then at some point it breaks up into these steps. And when I zoom in on any of these steps on an infinitely long chain, I just find more steps and more steps. This is so-called analyticity breaking transition. Nowhere is this curve differentiable. So wherever I look, it always breaks up into smaller and smaller points. It's not quite level staircase, but it's something very similar. It has this fractal structure for an infinitely long chain. This is what we found. Because basically when I zoom in, I see more and more gaps in the system. And it all happens at the same time. So let's try to develop a little bit of physical intuition why that is and why these gaps are. Okay, maybe before that I will tell you what he also found. Another way to characterize this is not in position space, but in frequency space. And so you can ask yourself, what's the lowest mode of motion, right, for this infinitely long chain? And so, of course, when there's no, this is now function, basically the frequency of the lowest motion mode is a function of the depth of the periodic potential. Of course, when the periodic potential is 0, the system is perfectly free to translate in space, so the eigenmode frequency is 0. I have no external traffic, right? So the eigenmode frequency is 0. This is the so-called sliding phase, it's free to slide. Now it turns out if I turn up the potential a little bit, the system is still free to slide. Because it still gets not, think of the one particle system, there's just one wave. And so up to some critical strength, the frequency of the lowest eigenmode is 0, and boom, at this point the particles localize, and now the frequency of the lowest mode increases very quickly, and out here it's basically the local oscillation frequency in the local parabolic range. And now what we found is that if I ask myself, what is the system with the largest critical strength, then it turns out that the golden ratio of U by A, if you want the maximally irrational number, is the one that pushes this UC out of phase. Before, I never really understood, why is the golden ratio any more irrational than square root of 2? Right? Somehow both are irrational numbers. Why does it matter? And in this system, one way to understand the physics of it is the golden ratio is the one that puts neighbors at maximally distinct location relative to the forces when you distribute them around the circle. So basically what you care about is not only where one particle experiences one force, the next neighbor experiences ideally an opposite force, but if I put the next neighbor at exactly the opposite force, then the third particle will experience exactly the same force. So the golden ratio is a way to somehow, in an average way, make the forces on all the neighboring particles at the most different. This is the prediction from Aubry. So let's go to the gaps and try to understand why this kind of structure occurs, where the final position avoids certain maxima. But it turns out it's not so hard to understand. I told you before, this 0 means the atom or the ion is exactly sitting on the maximum of the periodic potential. So basically, you know, at the top of the maximum, that's an unstable point, the ion will move either one way or the other. And it will avoid regions near the potential maximum. I will call this the primary gap, because basically whichever ion is sitting right on top of the potential will not like to sit there if the potential is strong. So this is the primary gap. So now as this first particle finds a new potential minimum, it will, via the spring forces, push its neighbors. Right? So basically, because this first particle doesn't like to sit in a certain region of space, the particle right next to it will also avoid the region of space, but a smaller region of space. Right? And then there will be the second particle over will form a tertiary gap and so on. So basically, these gaps are forming because one particle displaces and avoids a certain region of space, the next particle avoids a certain region of space, the next particle over avoids a certain region of space. And these gaps, it turns out, get exponentially smaller. And that's the physics of this breaking. Basically, if you want the perturbation, travels from the infinite chain. Now, we cannot make very long gaps, but we have looked at this with our system of two particles. And it turns out, if you think of kind of moving the system from right to left, and these gaps are exactly the jumps that we see in the friction force. So basically, these gaps are the same thing that we see as we make our hysteresis loops by moving the unperturbed ion position one way or the other. And so what we have then observed is we can see this primary gap. So we have plotted basically the delta x, the avoided position region color, versus the implied periodic potential. So here the ions are both localized, somewhere around 1 actually is this critical transition point, and then we see a gap opening up. This is the primary gap, and then we see, because this first ion avoids a certain region of space, delta x, the second ion avoids another region of space, which is about 10 times smaller. So basically, this is with a few particle system, the formation of these gaps forming the system. Okay, so basically, there's an intricate connection between the so-called superlubricity and nanofriction and this static model, which just says, you know, when is there a sliding relative phase, there's a pin phase. And for the first time, we have really seen it in a system, in an experimental system. So this brings me to the end of my talk. What would I like to do next? I think one interesting question is what happens in the quantum regime. So far, all I have told you is classical physics. I ignored the quantum part, correct particles. But in fact, our systems are so cold that we already occupy only maybe between the ground state and the first excited state of the system. So you can ask yourself what will happen in this system. And one thing that certainly should happen is that now the particle will not be released when the minimum disappears. It will be released earlier because it can tunnel through the barrier. So if I go through any of these pictures here, like in this one, then the particle can not only thermally hop across the barrier, it can also tunnel through the barrier. And nobody really knows what is the answer, what kind of phases are formed in the system. And moreover, nobody even knows whether quantum mechanics plays any role in the friction. Right? Can everything be described by a classical model, or is it some regime actually quantum tunneling from one potential well to the other one? So that's one thing that we would like to do in the near future. We're trying to see this tunneling and how it modifies the phase diagram. And you can ask yourself, what are the phases? Basically, what I call the sliding phase before in classical physics would be something like a superfluid phase. Something where things can move without resistance. And then there's a pin phase, which is like a localized phase. And finally, you could also think of adding spin degrees of freedom to the system. Where the particles can not only tunnel or move over, but they can also flip the spin. And then this gives rise to connect a variety of condensed matter physics systems, maybe to piles, to charge jams, to wave systems. And with this, I would like to thank you for your attention.
Yes, thank you very much, Vladan, for this wonderful talk.
true. So that's one interesting experiment. Another interesting experiment that they done with atomic force microscope is they took a graphite surface and they picked up a graphite flake. And then they saw sometimes when they rotate the tip and then move along, that they saw a reduced friction force. And it's believed for the same reason, if you rotate the periodicity of one to the other, you can reach something that is like a Boole ratio. In these systems, however, things were unstable because the graphite flake tended to snap back. There are also torsional forces. And so these experiments are not really reproducible on a one-by-one basis, but it's believed the same physics is working. What we have here is basically we can, for instance, vary the particle number from 1, 2, 3, 4, so we can really at least try to quantitatively understand what's going on. But that's a very good.
In the incommensurate Franklin-Ponderosa model, we could freeze out the internal degrees of freedom by putting on a large AC drive in addition to the DC. And that's an example of mode locking. And it would suggest that your system, where you have lower friction, when you have multiple particles, that if you put on a large AC drive, you can actually mode lock the system and get back to single particle behavior, which would be a high friction. That's probably an experiment you could do possibly for you.
That's very exciting. I hadn't thought about that. Because usually what people do is to reduce friction by, there have been experiments where people shake the thing and reduce friction by making it easier for the particles to thermally hop over. But I should look at this effort. That's a very exciting idea if that would actually happen where a small AC drive would actually stabilize the system. That's very interesting. Thank you.
You talked about static friction, but can you say something about dynamic friction and the role of avalanches?
That's a very good question. So avalanches are believed to have to do with frictional sliding on different length scales. If I understand correctly, in our current systems, I'm not sure whether they are big enough to actually see that. Although we can probably do measurements of maybe up to 10 particles in a vacuum. It's a very interesting question. So the question is how this propagation happens, what length scale is happening, and what these kinks are. So the eigenmodes of motions, I'm not sure you know are kinks. And it would be very interesting to see whether in a finite size system, one can see different length scale phenomena happening. You could imagine that first basically one part of the crystal gets pinned and then it slips and then that creates a larger perturbation that can move along. We haven't really thought about looking at that. At the moment we are looking at the multi-stable behaviors and even there that's very interesting. So, but that would be certainly something really exciting.
Okay, I see no more questions. Looks like everybody knows what friction is. Let's thank Vladan.